So in this class, we shall start with the concept of radius ratio. Now, radius ratio, often we say RR, usually this is defined as R radius of the cation by radius of anion. Now, the actual definition is radius. It is the ratio of radius of smaller ion to that of the larger ion. Radius of the larger ion. Radius of larger ion. Now, cations are usually smaller in size. Okay, since cations are smaller with respect to anions, since cations are smaller with respect to anions, so the modified definition is radius of smaller ion, that is the cation, by radius of larger ion, that is the anion. Okay. Now, from the knowledge of radius ratio, so what is the advantage of this radius ratio? By calculating the values of radius ratio, we can have some idea about the coordination number around the cation. So, by from the knowledge of radius ratio, the coordination number around the cation can be predicted. We can predict the coordination number around the cation, and from the idea of lattice type, and from the type of lattice in which it is crystallizing, actually, from the idea of lattice type, the coordination number of anion can also be determined. Okay, so from radius ratio, if we know this radius ratio value, we can predict the coordination number. Suppose this is the cation. We can predict the coordination number. Suppose this is the cation, we can predict the coordination number. Suppose it is 4, for example, like this. We can predict the coordination number if we have some knowledge about the radius ratio. See, we can think like this. Suppose if size of cation is small. See, if the size of cation is small, what will happen? Suppose these are the anions which are larger in size. You'll find that 4 anions will fit around this cation by concept of close packing. Okay, maybe 4 anions will fit around this cation. That is, coordination number is lower, coordination number is 4. So instead, if the cation is larger in size, so if the cation is larger in size, say for example like this is the size of the cation, then maybe it will be able to accommodate maybe 6 anions around it of same size. Size গুলো different হয়ে গেছে এখানে. So it should be able to accommodate maybe 6 anions. That means if cation is larger in size, it will prefer higher coordination number. Okay, so if the cation is larger in size, it prefers higher coordination number, and if cation is smaller in size, prefers lower coordination number. See, if the cation is smaller in size, then what will happen? Radius ratio will be lower. I mean, if this is small, the radius ratio value will be lower. That means if the cation is small in size, we know that it will permit lower coordination. That means radius ratio is lower, suggesting if radius ratio is lower, coordination number is lower. Similarly, if the cation is larger in size, the radius ratio value will be higher. And we know that if cations are larger in size, coordination number is also higher. Okay, so this is the basis of radius ratio rule. So often uh, they can ask question like this: what is the basis of radius ratio rule? What is the basis of radius ratio rule? So what is the basis of radius ratio rule? It's like this. So if size of cation is small, radius ratio will be lower, coordination number will be lower. তাই তো? তার মানে আমরা এইভাবে লিখবো যে if radius of cation is smaller, radius ratio is lower and coordination number will be lower. And if radius of cation is larger, then radius ratio will be higher, and coordination number will also be higher. So from the knowledge of radius ratio rule, we can have some idea about the coordination number. Now it can be shown that if the radius ratio falls in the region of 0.150 to 150 to 0.225 is actually 0.155. 150 na bole 0.155. If it is in the ratio of 0.155 to 0.225, then coordination number, observe coordination number around the cation, obviously. Coordination number of cation, this is 3. The geometry will be planar trigonal around the cation. Now if it falls in the region of 0.225 to 0.414, then coordination number is 4 and the geometry around the cation will be tetrahedral. When it is in the region of 0.414 to 0.732, the geometry by the coordination number of cation is 4 and the geometry around the cation is octahedral. And in some cases, special cases, it is square planar. This is in some special cases. Okay. And in some special cases it will be square planar, but we shall consider only this. We will omit the square planar geometry for the time being. And when it is 0.732 to 1.000, coordination number is 8 and this is cubic around the cation. So the geometry is cubic around the cation. And if it is greater than 1.000, this is coordination number 12. This is cubo-octahedral. Now we shall not go into this cubo-octahedral. We are interested at your level. We are interested with up to this. Okay, up to cubic. So if you are asked to explain the basis of radius ratio rule, so you have to explain the entire thing. This is the basis of radius ratio rule. Okay, so this can be calculated. It can be calculated. These are calculated values. Assuming calculated values, assuming close packing of hard spheres. Close packing of hard spheres. Okay, assuming close packing of hard, that means cations and anions, they are hard spheres and they are closely packed. Now, uh, they can give you also the derivations for these values for different structures. অর্থাৎ coordination numberটা 3 হলে why this radius ratio value will be like this. So they can ask you this question. So let us find out the we will actually calculate the limiting বা minimum radius ratio for coordination number equals 3. Okay, so limiting radius ratio for coordination number 3, of course, with respect to cation. Whatever we are doing, that is with respect to cation. Limiting radius ratio with respect to cation. So we can think like this. Suppose these are the anions which are larger in size. Now these anions, they are closely packed like this. Suppose the anions, they are closely packed. These anions, they are closely packed. These are the centers of the anions, and the cation is actually placed in the interstitial site like this. Okay, so the cation is actually placed in an interstitial site. Now suppose we can say that this is maybe A, B, C. If we join these centers, it will become an equilateral triangle. একটা equilateral triangle হবে এবং দেখো এই পজিশনটা, this position, let it be O, and if we join this AO and extend it, it will meet this at D. এবার আমরা যদি বলি দেখো এই যে radius of cation, radius of anion, let R minus equals radius of anion বা R plus equals radius of cation, and R minus equals radius of anion. এখন আমরা যদি বলি let A equals side length of the equilateral triangle, তাহলে আমরা বললাম এটাকে side length of the equilateral triangle. তাহলে দেখো আমরা এখান থেকে যদি দেখি তাহলে এইটা তো r minus radius of the anion, এটাও r minus radius of the anion, these are r minus radius of anion, r minus radius of anion. তাহলে আমরা বলতে পারি যে therefore twice radius of anion equals a, that is the length of the sides of the equilateral triangle. এবার দেখো আমরা AD দেখো in equilateral triangle, if you extend this will actually become perpendicular. So we can say from geometry AD perpendicular BC. Therefore আমরা বলতে পারি দেখো যে AD square equals AB square minus BD square. তাই তো AD স্কয়ারটাকে আমরা বলতে পারি AB স্কয়ার মাইনাস BD স্কয়ার. তো AB স্কয়ার মানে দেখো this is A square minus A by 2, this will be the midpoint as per geometry. So this is A by 2 whole square. Right? So this equals, therefore AD এডি এটাকে আমরা বলতে পারি যে দেখো এখানে √3a/2, ঠিক আছে তো? তাহলে এডিটাকে বলতে পারি √3a/2। নাও হোয়াট ইজ এডি? লুক কেয়ারফুলি, এইটা হচ্ছে যদি পয়েন্ট ও হয়, আর এই হচ্ছে আমরা দেখাচ্ছি দিস ইজ দি অ্যানায়ন, এটা এ, এটা ও, আর এইখানে গেছে ডি, এটা হচ্ছে ডি, দিস ইজ ও, তাহলে এইটা হচ্ছে ও, এই পারপেন্ডিকুলার গেছে। কারণ আমরা তো জানি যে এও, দেখো এও, দেখো ওটাকে আমরা কি বলতে পারি? দিস ইজ দ্য সেন্ট্রয়েড অফ দ্য ইকুইল্যাটারাল ট্রায়াঙ্গেল। তাহলে আমরা তো বলতেই পারি এরকম যে এও দিস ইকুয়ালস কত? AO equals how much? This is 2/3 AD, 2/3 AD, 2/3 of AD. Now what is AO? দেখো what is AO? AO মানে হচ্ছে দেখো এইটা, এই পোর্শনটা এখান থেকে এত অবধি, this is the radius of the anion, আর next um, this one এইখান থেকে এত অবধি, দেখো this is the radius of the cation. So AO, this is basically the radius of cation plus radius of anion. This equals 2/3 of AD. What is AD? AD হচ্ছে এটা 2/3 of √3/2a, তাই তো? 2/3 of √3/2. So therefore we can say that, therefore R plus R minus equals, we can say like this, this is what? 1/√3. Now what is R minus? এটা হচ্ছে a আছে, সরি, এখানে a আছে, √3/a, a/√3 হবে। Now what is R minus? R minus equals a/2. So from here we can write R plus R minus by R minus. So R plus R minus divided by R minus, this will be given by root a/√3 into 2/a. So R plus R minus equals 2/√3 minus 1. So this value comes to 0.155. So this is the minimum radius ratio for coordination number 3. Now it is very important, you must mention, now when you are asked to find out the limiting radius ratio, you must mention assuming that the ions are hard spheres, and closely packed, assuming that the ions are hard spheres and closely packed. এটা বলতেই হবে কিন্তু, otherwise the entire discussion is meaningless. You have to mention this, assuming that the ions are hard spheres and closely packed. Okay, so this is the limiting radius ratio for coordination number 3. Now let us move to coordination number 4. Okay, so for coordination number 4, so minimum radius ratio for coordination number equals 4, অর্থাৎ for tetrahedral structure. So often they can ask you to find out, question এরকম দিতে পারে, find out the radius ratio for Woodside, but find out the radius ratio for Woodside বা জিঙ্ক সালফাইড, যে কোনো একটা উডজাইড বা জিঙ্ক সালফাইড বা জিঙ্ক ব্লেন্ড স্ট্রাকচার। ঠিক আছে, to find out the minimum radius ratio for woodside বা zinc blend structure. Now how to find out the minimum radius ratio for tetrahedral. So you have to find out the minimum radius ratio woodside structure বা zinc blend structure means the geometry is tetrahedral. So you have to find out the radius ratio for tetrahedral geometry. Now tetrahedron, how to draw a tetrahedron? You probably know that tetrahedron is actually half of a cube. That means if you draw a cube like this, suppose this is a cube. Now if you look at, you know that there are 6 square faces. In a cube, you already know that there are 6 square faces. Now which are the square faces? See, suppose if you look at this face, এই দেখো উপরে একটা আছে, this is a square face, this one, that ঠিক, this is another. So in a similar way, this is another square face, just opposite এই একটা, and the other square faces above and below. So these are the square faces. Now if you consider, if you look at the uh, suppose if you want to construct a tetrahedron, so these two substituents by anions, they are occupying these two opposite corners of this square face, and the other two substituents, they will occupy just diagonally opposite corners, and the center, at the center will be the cation, that is the central ion. Central ion is the cation, of course, here. So if you look carefully, see, this is a tetrahedral geometry, tetrahedral structure. Okay, so we need to find out the radius ratio for a tetrahedral geometry. See, first of all, minimum radius ratio. First of all, look carefully. Suppose this is A, B, C, and D. Now, if you look at this square face ABCD, see, there is an anion here and another anion which is just in the diagonally opposite face. So it's like this. So this is an anion and there is another anion which are just in diagonally opposite faces. Sorry, which are at the corners of the diagonals. ঠিক আছে, তো তার মানে এইটাকে আমরা বলছি A আর এটাকে বলছি this is C. আমরা যদি বলি let A equals side length of the cube, A equals side length of the cube. Suppose A equals side length of the cube. So we can say that this diagonal AC, this equals square root of what? AB square plus BC square, অর্থাৎ A square plus A square. So this is AC equals root 2A, right? And you know that this AC, this is known as face diagonal. এটা তোমরা নিশ্চয়ই জানো, ফেস ডায়াগোনাল বলে, মানে যে কোনো একটা ফেসের ডায়াগোনাল। এবং what is AC? দেখো, AC equals radius of anion, এটাও radius of anion, তার মানে AC equals twice radius of anion. So we can say that radius of anion, this equals A by root 2. So this is equation 1. Okay. Next, let us consider this body diagonal. Suppose this point is the corner point. Suppose this is A dashed. and the center of this cation, let it be O. So if we want to draw the body diagonal, okay, see, if you look carefully at the body diagonal, so this is the anion, so this is the cation, this is A, O is the center of the cation, and it meets the other end at A dashed, like this. So A dash, this is the body diagonal. A dash, this is the body diagonal. Now, if you look carefully, this A dashed, we can write like this. A dashed, using Pythagoras, we can say that this A dashed, this is root of AC square plus CA dash square, using Pythagoras. So we can say that this is what? This is root of AC square plus A dash C square. Now what is AC? What is AC? AC is what? Root 2A. এটা বার করলাম আমরা. And this is what? A side length. CA dash যেটা by A dash C. So we can say that this is twice A square plus A square. So this equals root 3A. This is the body diagonal. Now we know that AO, this is A dashed by 2, because O is the center. So this is what? Root 3A by 2. Now what is AO? Radius of anion, and this is radius of cation. Therefore we can say that this AO, radius of cation plus radius of anion, this equals root 3A by 2. So this is equation 2. Okay, so dividing equation 2 by equation 1. Dividing equation 2 by 1. আমরা কি পাচ্ছি? R plus plus R minus divided by R minus. This equals root 3A by 2 into দেখো R minus টা কি পেয়েছি আমরা? R minus পেয়েছি দেখো A by root 2. So this is A by root 2. So this is root 3 by root 2. So from here we can write R plus by R minus plus 1 equals root 3 by root 2, or R plus by R minus equals root 3 minus root 2 by root 2. So this comes to 0.414. So this is the minimum value for coordination number 4. Once again, it is very important. Close packing of hard sphere has to be mentioned. Close packing of hard spheres. Otherwise, এই derivation করার পর তোমাকে কিন্তু marks deduct করবে. So I have mentioned many a times that accuracy is very important. Things are very easy. You should be accurate. Unless you write this, it is not meaningful. The geometry which we are doing is not meaningful unless you write close packing of hard spheres, which is applicable for the crystal lattice. Okay, so this is the radius ratio for woodside or zinc blende structure. Now next we come to say coordination numbers, or rather radius ratio. Minimum radius ratio for coordination number equals 6. So minimum radius ratio for coordination number 6, that means octahedral geometry. Now this octahedral geometry, আমরা বলতে পারি example given NaCl rock salt structure. Rock salt structure, তাহলে তোমাকে they can ask you question like this: find the minimum radius ratio for rock salt structure. Minimum radius ratio for coordination number 6 না দিয়ে তোমাকে দিতে পারে NaCl structure. Okay, so now this, if you look at the octahedral geometry, once again close packing of hard spheres has to be mentioned. Of hard spheres applicable for the cations and anions in the lattice. Eta বলার পর next we shall proceed. Always in all the cases we have to mention this first. Okay, so if you look at the octahedral geometry, say these are the anions, and this is the central cation. Okay, now if you look at this plane, okay, we will be interested only this planar portion only, because the rest you'll find that you can manage. See, it's like this. This is the octahedral geometry. Let us consider this planar portion only, A, B, C, D. So in this planar portion, if we assume close packing of hard spheres, okay, if we assume close packing of hard spheres, the situation is like this, and at the center will be the cation. These are the anions, and the center of the anions we can say A, B, C, and D. These are the center of the anions, and see, the cation is situated in this hole created by the anions. You can well understand that there is one anion above the plane of this, while there is another anion below the plane. Okay, so this is occupying an octahedral hole. Now let us join these. If we join, ধরো এই জয়েন করছি, A, B, C, D এগুলোকে জয়েন করলাম, and suppose this point B, O, and let us join AO, and if you extend this, it will meet at C, because it is a square. ABCD becomes a square, তাই তো? তাহলে আমরা বলছি since ABCD is a square, AO upon extension will meet at C. Now what is AB? আচ্ছা আমরা বলি let A equals side length of the square. A equals side length of the square. So we know that this is the radius of an ion. So therefore we can say twice R minus equals A, or R minus equals A by 2. So this is equation 1. And if we consider the diagonal AOC, okay, let us consider the diagonal. See, we know that AC equals root of AB square plus BC square. তাই তো? দেখো, this AC equals AB square plus BC square, অর্থাৎ this is root of A square plus A square, so this is root 2A. Now if you look carefully at AC, দেখো AC টা কিরকম আছে, এই একটা, এই সেন্টারে ক্যাটায়নটা, আর এইখানে আরেকটা অ্যানায়ন. So if you join these, this is R minus, this is also R minus, and this entire thing is obviously twice R plus, because it is the diameter of the cation. So we can say AC equals twice radius of cation plus radius of anion, and this equals root 2 by a, or r plus r minus equals a by root 2. So this is equation 2. So dividing 2 by 1. Dividing 2 by 1, we have we have r plus we have r plus r minus by r minus equals what? দেখো, এটা a by 2 আছে, তাহলে এটা আছে a by root 2 into a by 2, তাই তো? So this equals r plus r minus equals what? 0.732. So this is the minimum radius ratio for coordination number. Sorry, এটা আসছে, হ্যাঁ, this is the 0.414. কত আসছে এটা? Just a minute, আমরা ভুল লিখলাম, হচ্ছে না জিনিসটা। Just a minute, I need to recheck. This value is not 0.414. This will be 0.225. Okay, this value will be 0.225. This is for tetrahedral, and so this value will be 0.414. This value will be 0.414. So this is the minimum radius ratio for coordination number 4. Coordination number 6, octahedral coordination.